Everyone, so let's take a very simple example downloaded from the internet to illustrate some features that are very important in machine learning but not well documented. So we'll start with the Jupyter Notebook, and as you can see in my system I have started Anaconda, and from Anaconda I have started the Jupyter Notebook. I have created a Conda environment, and these are all the very fundamentals that every machine learning data scientists and data engineers will be knowing. So we'll start by importing the necessary packages, and then we are going to download some data from this particular site. And as you can see, the name of the file is wine.data, and this particular data contains about 13 to 14 variables, as you can see here, as columns. And there is a class label, basically which class the wine is belonging to. And there are some independent variables, right? What we mean by independent variable is, you can see that the alcohol part of the wine is not related with the malic acid in any way, but when all these things are combined, then that predicts the class label of that particular wine. So these are all called independent variables, and the one which we are going to predict, basically the class label, that's called a dependent variable. So always the machine learning objective is to find out the possibilities or predict the values that are viable for the dependent variable from a set of independent variables. So we create this and then we execute this particular code. As you can see, the data is being displayed because I called the head method, which is showing you the first few rows, and then you can see all the columns, and you can see that the class label is 1. So these are all belonging to class 1 category of wines. Let's see how many different categories are there, but just running unique on this particular data frame, pandas data frame. And you can see there are 3 different types of values, 1, 2 and 3, right? And then what we are going to do is that, as usual with any machine learning code, we are going to divide the data into a test data and the trained data, and we are taking the ratio as 30% for test, 70% for the trained data. And then what we are going to do is just look at the dimension of the data, and then let's look at what are the possible values that we have for the class label. 0 means the first column. Array always starts with 0 in pandas, and then you can see 1, 2 and 3 as we have seen earlier, right? And then let's try to do some pre-processing of the data. So from here onwards, our objective of this particular presentation starts, right? So whenever you are having some independent variables and you want to feed it to a machine learning model, always not necessary, but mostly you might be needing some pre-processing of the data, right? You may want to check null values, if you may want to check the balancing of the data, you may want to check the scale of the data, etc. These are all called the pre-processing methods, right? One such preprocessor is to apply some scaling, but let's see what is the effect of it. So without doing this pre-processing or normalization of the data, if I execute it, I get a certain way by which this particular data is distributed. But if I apply a preprocessor called min-max scalar from the scikit-learn library and then try to do a fit and transform of that particular data, and then try to plot the data, you can see the previous graph and this particular graph charts are different, right? Why? Because it scaled the data in a convenient way how we asked it, right? Another scalar that you can use like min-max scalar is a standard scalar, right? And then you can just look at how the data is distributed between the two kinds of scalars, right? For this example, let's use this standard scalar, and the model is very simple. We are going to use logistic regression with L1 regularization for this particular data, and we create the trained data and the test data, and we measure the accuracy. That's all. And this is what we do normally in all machine learning algorithms. You will tell the model to score by using the trained data with the preprocessor applied already, and then you are telling to score the test data and then find the accuracy. As you can see here, it's not so bad, and my data size is very small, but we got the training accuracy and the test accuracy. So let's proceed. We want to predict it now for a particular data that is coming in. So let's take the example data that is already there in our data frame, and then let's try to predict it. And you can see that the output is 1, which means that the first row of the data is basically this particular row, and you can see that the prediction is correct, and it's a very simple example. You can give any data. Here we are confirming that the prediction output is exactly matching what the data is available. It is not just repeating that particular data, it has gone through that particular algorithm which we have mentioned and then applied the output. And now comes the questions. This is good, this is pretty good to create a predictive model output for any kind of data. But what are the drawbacks of this approach? Whenever you want to apply this algorithm to some data, you will have to go through all these steps: the preprocessor, the scalar, and then you have the model prediction. And if you want to convert finally this one into some readable form, then you may have a post-processor as well. So the pre-processing, the model scoring and prediction, and then the post-processing. All these things has to be repeated each and every time, and this is just a simple Python program. A Python code can run on one computer. How will you distribute this when you are having millions and millions of rows of data? Instead, assume that if suppose you are getting streaming data, how are you going to transform this particular code? Basically, you will have to add so many constructs around it, and then you have to add so many hookups, and then you have to create your application, right? Let's see whether any other simple way is there or not. This is where we are introducing MLFlow. MLFlow is coming from the same company that started Spark, and it was created by the creator of the Spark, Mate Saharia. And recently they have contributed MLFlow project to Linux Foundation, and it's open source. MLFlow project was having 3 components earlier: MLFlow projects, MLFlow tracking, and MLFlow serving. The latest versions added one more called MLFlow registry, which allows you versioning of your models. We don't want to go too much into the MLFlow fundamentals. You can just go to their website mlflow.org and then go through the different components that are available there. So on my system, as you can see here, I have got the MLFlow server and the model server. MLFlow server is nothing but the tracking server, and then I have got the model server. Both are running. Now, having seen that, let us now revisit our application. So I am going to write the code from the beginning. Let's download the data as usual, right? And let us drop the column that we are going to predict. Why? Because we want the data that is used for training is trying to get the relationship between all the independent variables and then try to predict the dependent variable, which is the class label. So omit the prediction attribute, right, class label, and then create your x and y sets by giving 70-30% as we have done earlier, right? And now comes very, very important point which I was waiting for. All right, when you are creating a standard scalar, earlier you created the standard scalar and then you applied a fit and transform. Here we are going to define a function which is going to do the scaling of the data. Assume that you are doing a fit and transform within the function. What can happen? If this function is externalized, microserviceable. Then every time whenever you are passing a data frame, it will go through the scalar creation as well as fit and transform for that data which is passed at that moment in time. But we don't want that in machine learning. In machine learning, we want the scalar that has applied the transformation on the training data, and exactly that same scalar should be used within the function in order to predict the output of the new data. But if you do fit and transform inside the function, that will not happen. This is where you need to preserve the state of the training in your externalizable function. If you don't do that, you will get wrong results. And how will you do that? Never write an initialization and a fit and transform inside this particular function. Instead, initialize the object before and just apply the fit on that particular object and use that object inside the method to transform. So now whenever data is coming in, irrespective of whether it is a training data, test data, validation data or new data, it will go through the transform of the scalar which has been created earlier or which has been trained with the real training data. So remember that fit should be called outside the method which is going to be externalized. And now I am going to call the xtrain clean and xtest clean with this particular function that we have written, and let's execute these codes that we have written, right? And we are here and we have got it, and now comes MLFlow. So what is MLFlow? MLFlow is allowing you to expose a model as an API. So first let's see how that API part is working. Now there are problems. If you are exposing the model for serving as an API, you can just expose the logistic regression model. But if you do that, then your pre-processing and, if any, the post-processing are not going to be the part of that particular exposure. So what do? Just now we have written as pre-process function, and what we did is that we are wrapping the model in a kind of class which is called a Python model as per the MLFlow specification, and we wrap the model as well as your fitted scalar, which can then be fed into the preprocess method. So this wine model that we have written is now a complete self servicing kind of function which has got a preprocessor with a state, our fitted scalar, as well as the data. And if you have a post process, include that as well, and the post process definition is written here in this example. Whenever the output is 1, I want to give it a more meaningful output to the consumer, telling that okay, 1 means it is class label 1 wine, otherwise it is class 2 wine, and if anything else it's class 3 wine, that kind of stuff. So I wrote that pre-processor as well. So we have a pre-process as well as post-process as well as our model prediction combined together into a unit. Can you do it differently? Yes, you can. How will you do that? You will save that into a pickle file, for example, the fitted scalar that we discussed earlier, and then you will try to load that particular state while you are executing your pipeline. But the whole problem is that then that pickle file has to be traversed along with your model deployment wherever you go. But if you combine it into a single unit like this wine model, then you don't have to worry about separate pickle files, packaging it, and making an assembly of all these things together. Alright, so that's our wine model, and let's execute the wine model now, and then let us execute the preprocessor as well, which is also part of that model. And now comes another important point about MLFlow. MLFlow is created in such a way that If you have installed MLFlow, then it will use the underlying MLFlow context for running this particular application. But if you have not installed, it can create a Conda environment for you from scratch and then execute your model. That's a nice architecture. So, MLFlow should know what are the things that you are using, what are the packages that you are using in your model prediction code, and that's what you do by specifying a Conda environment as you have seen here. So, that's done, and the final step is now you created your model, you created your Python model as wine model, we called it as wine model, and now we are going to run this particular code, and today is August 30th, and I am going to change this August 30th, and this is my first experiment today. So, you are going to do the runs, in machine learning this is very important, you will be doing multiple runs in order to find out and tune your model, right? And each runs are going to be registered into MLFlow. Fantastic that is, because anybody, the peers, the colleagues, the supervisor, everybody can just look at how your model was performing, and if somebody else is doing an R model or a Spark model, those also can be exposed, and then you can do a model comparison in MLFlow. So, we are going to execute that particular code by submitting it into MLFlow, and that's done. It was very quick, and as you can see here, it has created a new experiment for me. How will you see that? Open the browser and go to your MLFlow URL, and this is how the home page of MLFlow will look like. You can see all my experiments, and then if you are refreshing this particular URL localhost colon 5000, which is the default port, then you will see that I have got August 30th first one, which I have executed just now. And if you look into that, you will see that my Python model that we have discussed earlier as a complete package has been deployed into it. Just click on that, and then you can see the accuracy and the AUZ score of your model, and you can see that model has been loaded as artifacts into this particular system. And if you look at your Conda YAML file, this is what is getting generated from the Conda environment file that we have written earlier. And you see this pickle file, this is just one pickle file which is comprising your preprocessor, post-processor as well as your model. So, you have got the model here, and then you have got a YAML file, and then you have got the pickle file. Let us just look at the model URL. I am going to copy this model URL, and I am going to come to the environment where my MLFlow model serving is running. I am going to close the existing one, and I am going to execute the command where that particular URL which I just copied, I am going to paste it here, and I am telling that please serve this model as an API. And this is the model that we have just copied, and then press enter and give it a few seconds so that it will start the model and it will wait. Great, we are now ready to test the real-time invocation of the model. How will we do that? Just to go back to your code, and we are now going to make an HTTP request to that URL API, because MLFlow server, model server exposed it. So, let us execute that one, and then we are going to tell that okay, take the first row of my data and now please give me the output by calling this URL, and make sure that I am getting the output which is now giving me the post-processed output data as well. So, I got class 2 wine. Yes, this is a prediction. It was different from the earlier prediction, that is okay. But what we have illustrated here is the way in which the state affinity is preserved by the model, as well as how to do the pre-processing, post-processing and model together packaged. Alright, so far fantastic. Now what is the next problem? The next problem is, oh, everything is running, API call one by one. What happens if I am getting some 500 million rows and I want to execute it? Calling an API 500 million times is not a good idea, and that is where Spark is coming in. So I would like to distribute the same code that we have created into Spark now. And Spark fortunately provides a fantastic mechanism for that. That's called PySpark Udf. And the greatest advantage is that if you have written a Python model, it can automatically be converted into a PySpark Udf in your code. But before doing that, let's start Spark, and as you can see in this particular screen, I have got my Spark code running. So master and the slave. It is a true Spark cluster on one machine. And the other proof is that if you are going to the localhost 8080, which is a Spark web UI, you will see that my Spark is running with one worker and one master. Currently, no applications are running at all. These are all my earlier runs. Oh, this was at 4 a.m. Alright, so we have got this Spark running, and now what we are going to do is that we are going to make a connection from the Jupyter to the Spark, and well, it is easily possible by using this particular code snippet where you define the PySpark Python, PySpark driver Python, and the PySpark.zip, and then connect to that particular URL you have just seen. And one of the most important thing is that don't forget to enable Apache Arrow, the latest and the greatest technology for transferring the data without serialization and deserialization. Apache Arrow is tremendously improving the way in which Spark reads the data, converts into pandas data frames. Earlier versions before Arrow enablement, the data frame calls in Spark is almost dedicated through the driver, where driver is collecting all the data and then creating the data frame, whereas when you are doing this arrow based memory mapped IO, it is much faster. Alright, so let's execute it and let's see whether it is working. So when we are running this particular code, you can see that I am going to get the connection and telling me where is my Spark UI, which is the port that you have seen. The default port will be 4040, in this case it's 8080, and then you can see the master URL and the name of the program, whichever I have written here, one-click batch execution, that's the name of the application. Alright, now what we are going to do is we are going to predict the model output by creating a MLFlow PySpark UDF, and the way to create is call the Spark_UDF on MLFlow PyFunc and just give the same URL that you have used. So I am going to remove this and I am going to paste the value that we have just copied from the MLFlow model URI. Save that, and what I am going to do now is I am going to run this particular prediction for the particular column of the first row of that particular data, and then run this particular code, and then after completing it, just look at the result of this particular data and see whether we are getting the correct result or not. Absolutely, and it predicted class label 1 wine by taking all this data. So by writing a single function with the preprocessor, postprocessor as well as the model, you have now created a fantastic application which can serve as real time, and the same application without changing the code with a very minimal effort of few lines can be converted into a Spark based parallel distribution for scaling into innumerable amount of data. And now if you are not liking the way in which I did in Jupyter, don't worry, you can just go to your normal algorithm, and this is the complete code which you will write as a Python file when you are writing as a standalone program, not on Jupyter. And you see here I have done exactly the same thing, and all I need to do is in this particular code, again what I am going to do is coming here and remember we changed that URL because this URI is my is the testing that I did earlier. So I am going to change this particular value to the new value that we had copied from the MLFlow model serving URI, right? So let's change that one, right? And save that, and what we are going to do is just run a command spark submit --master, give the master URL and your code. And let's execute it. Now the application is running on Spark. It is distributed. As you can see, just like any Spark application, this particular code is now getting executed. So give it some time and then let's see what is happening. All right, I should have killed this particular code because there is one more Spark context running there. So what I'm going to do, I will just kill this particular kernel, right? And you can see that the Spark application is now running. Wow, it is giving me, as you have seen in the code, I am just looking at the first 10 rows and it is predicting the result as class label 1 wine, etc. for all these rows. Hope you enjoyed the session. Read my article on Medium on this state preserving for getting the full details about what we have just seen. Thank you very much.